Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at our homework for lesson 2.2.5. We're going to start off with the M&Ms for modeling the multiplication of fractions using a rectangle for that model. So one way to model multiplying fractions is to shade a unit rectangle. So by unit rectangle, they mean that this rectangle refers to one whole unit. Okay, so if you take 2/3 times 2/5, the first thing you'd want to do is break this unit rectangle into 5 equal parts, and 2 of the 5 equal parts would be 2/5 of the whole. So now we just shade in 2/5, so this is a representation of the fraction 2/5. Now to find 2/3 times 2/5, it's good to think of it in terms of 2/3 of 2/5, because the word of in this context refers to multiplication. So if you're going to find 2/3 of 2/5, then we can now break that same unit rectangle into 3 equal parts horizontally in the opposite direction that we did for the fifths. And you can see that this section right in here represents, I guess that right there, that represents 2/3 of this entire section that's been shaded in. And that entire section that was shaded in represented 2/5 of the total, or of the whole unit rectangle. So when you break this down, these 4 parts represent 2/3 of 2/5 of the whole. What you end up with is 4 out of the total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the total number of rectangular parts inside here is 15, and the 2/3 of 2/5 represents 4 out of the 15 total parts. So that's how you get an answer of 2/3 times 2/5 is equal to 4/15. Now, in a lesson, you're going to see that, hey, isn't there a shortcut we could use here? Wouldn't it just be so much easier if we could just multiply the numerator times the numerator to get our numerator and our answer, and the denominator times the denominator would give you the denominator of our answer? And the answer to that is yes. This is showing you why we multiply the numerators together and the denominators together to get our answer when we're multiplying fractions. So there's different rules for adding fractions together than there are for multiplying them. And this kind of represents why we do what we do. All right, so Frida Friendly works for a local car dealership. She noticed that 3/4 of the cars are sedans. Those are like the family cars with 4 doors, and that half of the sedans are white. So use a unit rectangle to represent this situation. So, okay, so this entire rectangle is going to represent all the cars in the dealership's parking lot. And if you break it up into 3/4, everything that's been shaded in red represents the sedans that are on the parking lot. Half of the sedans are white cars. So I'm going to shade in this direction in blue for all the white cars that are sedans. So after looking at all this, this is basically 3/4 of 1/2 or 1/2 of 3/4, either way you choose to go. 3 of these sections have been double shaded, both red and blue. So 3 out of the 8 total sections that represents all the cars on the parking lot are white sedans. Okay, so let's look at the equation that we use. 3/4 times 1/2, or we could have written it as 1/2 times 3/4. If you're thinking 1/2 of the 3/4 cars that are sedans equals 1 times 3 is 3, 2 times 4 is 8. So 3/8 of the car are white sedans. And then it's just a matter of converting that to a decimal number by dividing 3 by 8 and converting it to a percent by rewriting 3/8 as a fraction out of 100 using proportional reasoning. And it turns out when you multiply 8 times 12.5, you get 100. So we're going to multiply 3 times 12.5, and that will give you your percent. In parts A and B of problem 89, the rectangular models for 1/2 of 1/4 and 1/4 of 1/2 look different, but the answers are the same. Okay, so read the steps in the math notes in this section to calculate 2/3 of 2/5, and then do the same thing for 2/5 of 2/3. So remember, when you're multiplying numbers together, it doesn't matter what order they are in. 2 times 3 is going to give you the same answer as 3 times 2. That's supposed to be a 2 there. Horrible looking 2. Let me fix it and make it look nice. Oh, why'd I do that? Oh, you're killing me. Killing me. Sorry. Either way, they're going to equal 6. So here, same thing with the fractions. 2/3 of 2/5. If I take 2/3 of this entire big rectangle, I've shaded that in red. There's 1, there's 2 out of the 3. And then I take 2/5 out of the 2/3. Here is 1/5, 2/5, 3/5, 4/5, 5/5. So break that section into 5 equal parts and shade in 2 of them. You end up with 4 out of the 15. So 2/5 times 2/3 is 4/15. Same as 2/3 times 2/5 is 4/15. All right, simplifying each expression below. This is an absolute value problem, so you have to do this first. 10 plus 2 is 12. The absolute value of 12 is 12. So now when you add -32 to 12, you're asking yourself, do you have more positives or do you have more negatives? And the answer is you've got more negatives. How many more negatives are there? How many more is a subtraction question. So we will subtract away all the positives that would have met up with negatives here to form their 0 pairs and go off on their honeymoon. So you're left over with 20 negatives after the 12 negatives left to go on their honeymoon with the 12 positives, right? The 12 0 pairs. So our answer to this problem is -20. Here, it's probably best, I think, add these guys together first, but you can technically do it in any order that you want. You can go from left to right. And actually, okay, I see why I chose to add these guys together first, because when you're adding 2 numbers with different signs, you're going to do a subtraction, and it would be a lot easier to just subtract 1/3 from 1/3, and then 17 from 50 to get you -33. Otherwise, if we would have done this portion first, we would have had to add these 2 mixed numbers together and find a common denominator, which is more work, which is fine. You could have done that, but I just think it's probably easier to do it this way. And now that you've got 2 numbers with the same sign, you're just going to add the numbers and keep the sign. So 33 plus 5.5 is 38.5. And since they're all negatives, it's -38.5. And then same idea here. The idea of, instead of subtracting a 1.89, add the opposite, use that KFC process. Instead of subtracting a positive, add the opposite of whatever that number is. Now, maybe we'll add the negatives together first to get -7.26. And then at the end, do the subtraction because you're adding a positive to a negative. And you've got more positives than negatives. So how many more? Do the subtraction and you get 88/100ths. And that should be positive 88/100ths because you started with more positives than negatives. Once again, if you want me to go over this in a little bit more detail, just stay on the, on the Google Meet if we're meeting, or send me an email or ask me in class. I can do this to help you out. Do you think it matters what order you follow when performing math operations? Investigate this by doing the following problems. For the problem 9 plus 2 times 3, do you think you get the same answer if you add first as opposed to multiplying first? And the answer is no. If you were to add 9 plus 2 first, you would get the problem 11 times 3, which is 33. But the order of operations says you're supposed to multiply. That's the higher priority than adding. And the reason for that can be explained with Cecil on the tightrope, right? If he takes a step that's 9 feet, then 2 steps of 3 feet becomes 9 plus 3 plus 3, right? Here are the 2 steps of 3 feet. Well, how far did he go? He went 9 plus 3 is 12 plus another 3. is 15. So by using the order of operations and giving priority to multiplication first, you get 9 plus 6, which gives you 15. For this problem, 2 times 4 times 7, you get the same answer as if you started with the first two numbers as if you started with the last two numbers. In this case, it's just fine because all you're doing is multiplying. So the associative property of multiplication says it doesn't matter how you group these. There's no reason to give multiplication priority over multiplication because they're all equal. Whereas here, multiplication had the priority over addition, so you had to do that first. Here, it doesn't matter which part you do first. So 2 times 4 is 8, and 8 times 7 is 56. But if we had taken 2 times 28, you'd still get 56 as your answer. Either way, you get 56. So when all you're doing is multiplying, it really doesn't matter the order in which you do the work. You'll get the same answer. But when you start mixing multiplication with addition or subtraction, then the multiplication has to take priority. All right, which of the following numbers could not be represented as a probability? Well, there's no such thing as a negative probability. That doesn't work. So probability of 1, that means that something is certain to happen. Okay, if you've only got blue marbles in a bag, what's the probability of getting a blue marble? It's certain, right? It's 100% or 1. If you've got 100 marbles in a bag and one of them is blue, then you've got a 1% chance of getting a blue, which is not impossible. It's not certain. It is like, it's unlikely, but it's still a possibility, right? So 1% is a legitimate probability. And then in decimal form, 0.1 is 1/10, which means that's kind of like if you have 10 marbles in a bag and one of them is blue, this would be the probability that you would pull out a blue. There's just no way you can ever have a negative probability. That doesn't even make sense. Okay? All right, so that takes care of our homework for today. Let's go ahead and head over to our lesson. Take care. Bye. Bye.
Hey, feeling good.